Welcome, detective. Go ahead and step under the yellow tape because today we are diving straight into a full-blown incident report. We're looking at a specific case file that I like to call the failing high tariff question. This is the exact topic that consistently separates a B grade from an A star in Cambridge AS and A-level computer science. We are going to treat the exam paper like an active forensic investigation, looking at the exact spots where candidates are getting their marks completely stolen and how top-tier students lock those same marks down. Our main suspect today, binary addition and subtraction with Overflow. Now, I know what you're thinking. It sounds incredibly straightforward, right? It's just ones and zeros. How hard could it be? But as we'll uncover in this investigation, the way you document your process and understand the underlying hardware concepts is where the real battle in the exam room is fought. Just the other day, I was reviewing some mock papers with my two rookie forensics agents. We've got Agent Alex, who is absolutely obsessed with the loose footprints, the exact binary bits, the isolated facts, the calculation itself. And then we have Agent Sam, who ignores the math and gets totally lost in vague theories about computer crashes without providing any solid proof. Spoiler alert, they both lost the marks. Today, we're going to figure out why. I want you to pay very close attention to this exact insight, straight from the senior examiners. They're practically handing us the master key to decode exactly what they are looking for when they take their red pen to your paper. We're not just going to do some basic binary maths today, we're going to perform a complete autopsy on a perfect A-star answer. When you hit one of these high-tariff questions on Overflow, the examiner isn't just glancing at your final string of binary digits. They are forensically examining your understanding of the entire computer system's architecture. They want to see the microscopic evidence of your thought process. And that brings us to the fundamental challenge we are trying to solve in today's explainer. Why do so many capable students bleed method marks on these multi-step calculations? It really is a tragedy. It's like arriving at an exam room crime scene and seeing that a student did all the complex math perfectly in their head, wrote down the final answer, but made one tiny microscopic bit flip mistake on the paper. And because they didn't leave a trail of evidence, they lose all 5 marks in one fell swoop. By transforming these dry syllabus requirements into a rigorous systematic strategy, we are going to stop that bleed. We're going to build an impenetrable forensic exam protection checklist to ensure that your marks are never stolen again. To solve this case, we've organized our investigation into 4 distinct phases. Think of this as your forensic roadmap. Phase 1 is core principles and theory. Phase 2 is the method mark strategy. Phase 3 covers the top 3 examiner warnings. And finally, Phase 4 is mastering the evaluation phase. Let's process the scene. We'll kick things off with Phase 1, core principles and theory. This is all about moving beyond superficial knowledge and digging into the structural integrity of your answers. Let's look at the theoretical foundations required by the Cambridge Assessment Framework. The crucial point here, the thing that rookie Agent Alex just can't seem to grasp, is that examiners do not want isolated facts. They are actively hunting for connected understanding. They want to see cross-topic connections that hit multiple cognitive domains. What does this actually mean when we're dealing with binary overflow? Well, it means you shouldn't just know the rote definition that overflow happens when a calculation exceeds the maximum representable value. You need to connect that fact to exactly why it happens. What is the causal relationship? How does that specific bit carry impact the processor? Does it corrupt memory allocation? Does it trigger a specific flag in the status register? You need to be able to take that core concept and transfer it to a totally unfamiliar context given to you in an exam scenario, like an automated vehicle sensor system or a factory temperature control loop. If we whip out our UV highlighter and look closely at the grading benchmarks, we can clearly see what gets rewarded. On one side, we have superficial breadth. This is memorizing isolated facts without any context. This is the classic B-grade trap. A student writes, overflow is an error that makes the result wrong. Okay, technically true, but incredibly superficial. The examiner is not impressed. On the other side, we have the A-star standard, analytical depth. This involves applying logical, structured reasoning and mapping out the causal relationships. An analytical answer explains the architecture of the register, details how the binary addition caused the most significant bit to carry over into a non-existent spatial boundary, and explicitly states the effect that has on the status register. That depth, that chain of evidence, is your golden ticket to top marks. Moving into Phase 2, the method mark strategy. This is where we turn theory into an actionable, technical methodology that locks down your points. But before we crack the code and reveal exactly how to secure these method marks, let's pause the case file for a second. To ensure you never miss our weekly forensic investigation breakthroughs and always outsmart the examiners, make sure you subscribe to Ace the Exams at the handle @AceTheExams right now and turn on all notifications. Okay, let's get back to the scene. My two rookies, Alex and Sam, hit a massive roadblock mid-argument yesterday over how to format a calculation. Let me step in and show you the exact forensic reconstruction of a perfect answer. By following this standardized 5-step procedural sequence, you ensure that every calculation and data extraction is clearly justified on the page. You can actually pair this perfectly with the Peel template, point, evidence, explain, link, when you write your extended answers. First, deconstruct the question. What is the command word? Calculate, explain, or evaluate. Second, extract the relevant data, literally pulling the specific binary representations from the text. Third, select your analytical framework. Are we using 2's complement? Fourth, execute with crystal clear notation. This is your evidence. If you are executing a 2's complement subtraction, you don't just write the answer. You write down the inversion step, you write down the +1 step, you show the carry bit explicitly. And step 5, present your conclusion using the correct terminology. You link it back to the question's context. You absolutely must remember that this process acts as your primary safety net. Marks are awarded for systematic processing and clear working. If you just write down the final binary number and you made a simple, panicked arithmetic error in step 2, you score an automatic 0. The examiner has no evidence to give you marks for. But if you document your systematic processing, if you lay out the relevant principles of binary addition and execute your analysis where the examiner can follow your exact path, they can award you method marks for every single correct step you took prior to the mistake. You are building an undeniable case for your own competence. Now we're entering phase 3, the top 3 examiner warnings. We are pulling these fatal pitfalls directly from the principal examiner reports, giving us a live look at the most common exam room crimes. This is where we run our live forensic workshop. I want to run a quick interactive challenge with you right now. I'm conceptually putting a 60-second visual timer on the screen. Imagine you are reviewing an authentic source from a past paper. The question asks why a flight control system rejected a sensor reading after a calculation. A student wrote, "The system crashed, which caused an overflow in the register. Time's up. Did you spot the critical error?" That is our first examiner alert, confusing cause and effect. The system crash didn't cause the overflow. The calculation generated an overflow which caused the system crash. It's a fatal structural drop. Second warning, forgetting boundary conditions. Did you check the specific register size given in the scenario, like an 8-bit or 16-bit limit? Third, generic answers. If the prompt is about flight control sensors and you give a textbook definition of an overflow without mentioning the altitude data, you forfeit the application marks immediately. And lastly, confusing terminology, which leads perfectly to our next piece of evidence. Let's run challenge number 2. Take a look at this specific directive from the examiners. It's a non-negotiable rule. I'm going to give you a flawed student essay snippet. The student wrote, "The MSB changed, so the flag went up, showing the complement was wrong." Okay, pinpoint the technical mistakes that killed their grade. First, what is the MSB? Second, what flag? Third, what does "the complement was wrong" even mean in this context? If you are going to use acronyms or complex concepts like most significant bit, choose complement, or the carry flag in an extended response, you absolutely must define them briefly. The most significant bit, representing the sign of the integer, was flipped incorrectly. See the difference? That proves to the examiner that you are in total control of the academic vocabulary. Okay, we are moving into the final stretch, phase 4, mastering the evaluation phase. This is the final autopsy, where you elevate your answers from basic problem solving to top-tier critical evaluation. This 3-step loop is the ultimate framework for proving your algorithmic competence. We've talked about deconstructing the given information, and we've talked about solving the binary arithmetic and logical steps. But the top 1% of students, the true master investigators, always execute step 3, evaluate. They check their findings for reasonableness. Think about it. If you subtract a positive number from a negative number, and your binary result gives you a positive integer, your evaluation phase should be screaming at you that something went wrong. You should immediately recognize an overflow condition has occurred. You then use that evaluation to justify your recommendations on how the system's error handling routines should respond. When assessing algorithm quality or error handling methods, these 4 pillars must be the core of your evidence-based conclusions. If a high-tariff question asks you to evaluate a specific method for handling a binary overflow, you must discuss these metrics. Does adding an extensive error-checking routine increase the time complexity of the program? Does allocating larger 16-bit registers to prevent the overflow negatively affect the space complexity and memory footprint? How efficiently does the algorithm handle extreme edge cases? And ultimately, what is the total net effect on the system's performance? Now, if you encounter a comparative analysis question, say evaluating two different methods of binary subtraction or two different overflow handling routines, structuring your response like this exact matrix ensures you hit every single syllabus requirement. First, identify similarities and differences using specific comparative connectives like whereas, conversely, or in contrast. Second, provide evidence. Support every single claim with explicit data from the binary representations you just calculated. And finally, synthesize a conclusion. You have to draw a definitive judgment on which method is better suited for the specific scenario provided, weighing the relative importance of the metrics we just discussed. To ensure these rigorous, multi-step sequences actually stick in your brain when the exam timer is ticking down, I highly recommend using a visual story method. Don't just stare at dry strings of ones and zeros. Imagine the bits physically shifting through the processor's logic gates. Picture them hitting the hard physical boundary of the register and literally spilling over the edge, triggering a bright red flashing carry flag alarm. Encoding the cause and effect into a vivid mental movie prevents you from confusing your terminology and freezing up when the pressure is on. We've completed our autopsy. Agent Alex and Agent Sam now understand exactly how to engineer a full-mark paragraph. So, as you review your case files and tackle your next past paper, ask yourself this critical question. Are your exam answers merely presenting isolated facts, or are they proving a connected, analytical mastery of the whole process? Let's recap your forensic exam protection checklist. Deconstruct the command word. Show every single step of your working, define your terms clearly, and critically evaluate the final output for reasonableness. Don't let your hard-earned marks get stolen by superficial mistakes. To make sure you're fully equipped for your next investigation, subscribe to AC Exams at the handle @ACExams, enable all notifications, and comment below with your current level and your target grade. Thanks for joining me on this explainer, and keep practicing those past papers with a forensic eye. Case closed.